I'm going to talk about a combined path following controller. So basically, yeah, for the traction phase of a public kite generator. So basically, this is going to be my outline. And well, let's start. Well, I think everybody here knows what a public kite generator is, but basically we have two different phases. A power production phase, in which we want the kite to follow a fast crosswind motion, and another power-consuming phase in which we want the kite to basically withdraw the least power from the wind. Okay, in which in the power productive phase we reel out the tether and produce electricity, and in the power-consuming phase we reel the tether back in. Okay, I'm going to focus on the power productive phase, and well, in a path following controller, the first step is to define a path to follow. Right? And so the first step is actually path planning. I think there was a presentation about it yesterday. But basically, there are several ways to define a path. But well, we've been basically using first of kind of optimal control in a first approach, and then we transfer the resultant trajectory onto a 2D plane, a tangent plane, to this spherical surface. The spherical surface is defined basically by a center that's the ground station, and it has a radius equal to the tether length. Okay, so we're basically assuming there's no second. Okay. As an example, I'm going to use this kind of elliptical shape path. Okay, and so basically, and here we are talking about non-holonomic vehicles. Non-holonomic vehicles are vehicles that basically usually hold really complex dynamics. For example, our vehicles, such as a car, is a non-holonomic vehicle, are vehicles that basically cannot move everywhere. Right? For example, a car cannot move sideways. Right? It will be great for parallel parking, but it doesn't work like that way. And yeah, and in order to deal with these constraints, all predictive control is actually kind of an adequate method because it optimizes given performance, taking into account these constraints. Okay? But model predictive control, or MPC, is really difficult to implement because basically we're talking about real-time optimization. And so it's computationally heavy. So we, in order to approach this, to tackle this problem, we are thinking about using a combined controller, in which basically we have a basis controller, feasible, stable, proven to be stable, and we add an MPC term. Okay? This basis controller can serve as a backup plan when basically the optimization doesn't work, because we're dealing with it in real time, right? And it serves as well as an initial guess. Any optimization problem is faster to solve if we have an initial guess. Okay? And the MPC term is simply to improve the performance of the basis controller. So let's talk about our basis controller. We follow this guidance logic in which basically we want to compute the required centripetal acceleration for the kite or the vehicle to join a reference in the path. So here in this picture, the path will be basically this bottom line here. We will basically compute the cross-track error D from the kite to the path, and we will find basically Q, so basically the closest point in the path to the kite, right? From that Q point, we jump a given L0 distance ahead in the path, and we define our reference point R. Okay, this L0 is the only parameter that we need to tune in this controller. Okay? And then based on that R, that reference point, we define L1, that vector between the kite position and the reference point, and well, from that point we can compute the required centripetal acceleration for the kite basically to follow a circular path, circular trajectory, joining the path in R. Okay. This is basically our guidance logic, and we can basically simplify the dynamics in this 2D basically on top of the spherical surface that I talked in the beginning. We can simplify this model into this basically two dimensions as well, two-state model basically, and we have this guidance logic with saturation. Okay, so basically we have an unsaturated region S1 and we have two saturated regions, S2 and S3. Okay, and we basically on this guidance logic, we basically did a stability analysis. So basically, we proved that in the saturated regions, the saturated acceleration, so basically our guidance logic, will steer the kite to the unsaturated region, S1. And in this unsaturated region, we proved using the Lyapunov analysis that this controller or this guidance logic is stable. Well, this isn't really a control session, so I can talk a little bit what is a Lyapunov analysis. Basically, a Lyapunov analysis is the idea is to find an energy-like function that is basically zero when the kite is in the path, for example, for this case, and is always positive everywhere else. Okay, and if that time derivative of that function is always negative, except when in the path, when it is in the path, it's zero. If we can find that function, that time derivative to be negative, we can prove that basically the guidance logic will always steer the kite or the system to zero, so basically to the path. Okay? That's the idea behind the Lyapunov stability analysis. And that's what we've proven. Okay? And so basically, based on this guidance logic, we define the control law. And here in the path, we admit that we act on the roll angle. So basically the angle around the longitudinal axis of the kite. So basically like this. Okay. And basically we can find the first equation is basically let's say the lateral acceleration that is conveyed to the kite when we act on the roll angle. And if we set that acceleration and the acceleration that of the guidance logic, basically the centripetal acceleration to join the path. If we equal these two accelerations and solve for our roll angle, our control input, we can find a reference roll angle, and then we can define a control law, which is here with saturation. Okay. So basically, this is our basis controller. Now let's talk about the MPC term. Okay. First of all, I'm going to at least give a brief explanation of what is MPC. Okay. So MPC, this is the algorithm. So basically, we're solving at each time step. We measure the state, and we solve an optimal control problem. This optimal control problem, basically, we optimize for a given cost function. This cost function is basically the one on top. So we have a stage cost L and a terminal cost G. Yeah. And then we solve this optimal control. And well, basically from this optimal control, we get a resultant trajectory, predictive optimal trajectory. Okay? And from this optimal control, we also get predictive optimal control input over time. And we take this optimal control input and we feed it into the system. Okay? And then in the next time step, we measure the state again, and we keep on solving optimal control problems in every time step. Okay? That's basically the idea. In terms of MPC, a really important thing is to choose the parameters of the problem, of this optimal control problem here. So basically to define the cost functions, the state sets, etc. And here is basically what we've chosen. If you notice, for G and L, we basically used the Lyapunov function pair that was used to prove the stability of the basis controller. Okay? And why is that? Because this can also guarantee stability of the MPC term. Okay? This type of problem in MPC is usually called a quasi-infinite MPC. And it has some, we need to guarantee some certain properties of these, let's say, ingredients of the MPC to guarantee stability. One of the most important, at least, property to guarantee that stability is basically this inequality. So this basically means that, let's say, the rate of change of the terminal cost is less or equal than that rate over there that is linked to the stage cost. Okay, and this is usually used to prove stability of these quasi-infinite MPC controllers. And actually, we thought we had this. And I think in AWEC, I did quite a similar presentation in which I was pretty confident that we had this, but we don't really have this. So yeah, we had kind of a weaker condition. And part of our work now is to dabble with mathematics to prove the stability with this weaker condition. But I have some results, okay? And this is in a 2D plane. And the first one on the left is simply with a basis controller. And the other two are with a combined controller. So basically, you have to remember that the goal here is to follow the path more closely, okay? So, for example, in the middle, we have this MPC, combined controller, right? And we're following the path much more closely. But the control isn't really smooth, okay? It's reactive. And so I added kind of a penalty for basically the rate of change of the control input. And well, that's the result. Here I have basically the cross-track error over time for the basis controller only. And you can see that basically the cross-track error over time, that red line is basically the average over time. And I was able to decrease this average a little bit. Yeah, so basically those are the results. Future work, yeah, I need to work on my stability proof. I want to do simulations with more realistic, in more realistic environments, because until now we've been using kind of a mass point model in Simulink, but we've been starting to work with other simulation environments, and there's a lot of people here that have been working in AWES specific simulation environments. So yeah, I'll probably use some of those tools. And after that, we're going to do some field tests with our small prototype. Not really the prototype that Sergio showed, a little bit larger than that, but yeah, with our prototype. And then obviously performance assessment. Another thing that I want to work on is basically, so here I was focused on basically following the path more as close as possible. But that doesn't, in terms of power production, it doesn't really mean that it's the best way to go, if so. We suppose that the path is optimal, but we're a little bit out of the path. Maybe the right idea is not really to go back to the path, but maybe optimize power production in a given way. So I'm thinking, for example, of changing basically the cost function, the objective function of the NPC term, and work with economic NPC, which is basically NPC but with a cost function that describes an economic performance metric. For example, in this case, will be power production, for example. And yeah, that's it. Thank you very much.
Are there any questions?
Thank you so much for your presentation. I think I missed the point about the stability analysis of the NPC. Would you please elaborate a little bit more?
Yeah, sure. Usually in usually in this type of NPC architectures, we need to prove basically, when we say we want to prove stability, we're saying that basically at each time step, we need to prove that at each time step the full cost function, the stage cost and the terminal cost, decreases. So it eventually will go to
you are going to consider that cost function as a Lyapunov, for example, function?
Sorry? Yeah.
You are going to consider the Lyapunov
yeah, we're going to use the Lyapunov function. Actually, there is an interesting connection between Lyapunov theory and basically the proofs of stability of NPC terms. Basically, we're looking for the same properties as we're looking in Lyapunov functions in when we're talking about NPC stability for the cost functions. We're basically looking for the same properties. So we can basically kind of use one and the other for the NPC or for this control.
Thanks.
Yeah, thank you very much. If you want to catch in the coffee break. I was wondering, have the additive bit for the MPC control input, have you also tried alternatives to that? For instance, finding the sort of the minimal deviation to the existing control input?
No, I haven't tried it, but I think it's a good suggestion.
Thanks.
It's going to be, yeah, thanks.
Thank you for the presentation. I want to ask about your guidance algorithm. So because
About what, sorry?
guidance algorithm.
The guidance algorithm.
Yeah. So did you try another guidance algorithm because it affects the behavior of the controller?
Basically we've tried, but basically this one is an, we adapted it from another guidance algorithm that is from Park, I think, right? Which is called the L1 algorithm, which is quite similar, but for example, that L1 vector, the length is fixed. So basically, in that sense, for a controller, we had to have different regions. If we were in a L1 or less than that distance to the path, we could use that controller, but if we were farther away, we had to use another controller to reach the path. So we tried that one, and this is kind of adapted from there. But since here we're fixing L0 and not L1, this controller can work everywhere, right? We didn't need different controllers based on the distance to the path. But those were the only two guidance logics that we've tried. But yeah, that's a way to go. Yeah, trying other guidance logics.
Thank you again.
You mentioned that the basic algorithm is for backup if the MPC cannot be solved or the optimization fails. Does that happen sometimes in your simulations? That MPC cannot be calculated?
It does happen sometimes in correlations.
1% of the time, or?
Well, I'm not sure. It kind of depends. I've been, tweaking some parameters. For example, the prediction horizon. So basically, that's T over there in the MPC architecture. For example, if you change it, that alters when a problem is feasible or unfeasible. And so basically, it changes basically the rates of the ratio between successful optimizations and not. But so I cannot tell you how much, how many